That's easy. How can you solve it? Oh, simple. PR. We can write a straightforward way this Kirchhoff-Helmholtz integral equation, and then we just stop. Oh my God, how can I solve it? If you know the velocity on the plate, then we can solve it, right? That's easy. And also we can select this G in such a way that all this term will go away, right? And know the velocity and the G, we can get it. And then let computer calculate it. Okay. And the other way to understand the vibration of this kind of vibrating sphere is just using principle of superposition. And I can argue that the vibration of this is composed by this vibration plus this vibration plus, for example, this vibration. Okay? And again, I can argue that this vibration is a superposition of one piston vibrating that push back and forth the fluid particle that really push back and forth by this second mode. Okay? And I say this is equal this one plus another one. Right? So designing equivalent disk, right? And then I can use the solution that I obtained already by just changing the variable. And I can get it. And also I can get a solution by using designing equivalent vibrating piston. That's fantastic. And that's the fundamental concept that has been adopted in boundary element method. That's simple. Okay? And let's recall these two cases. That is similar with what we heard using four-speaker case, right? So this is the case, and we know the solution of this case, right? Solution is like exponential jkz minus exponential jkr. Okay? And I will teach you how to reduce the sound radiation from your cell phone. Okay? Make a cell phone like this, vibration of cell phone like this, right? Or maybe like that. As I indicated over there, there's a two piston oscillating. And because there is a phase difference, some sound canceled over here. But in overall, it decays like a monopole. And the cancellation effect by this quadrupole type vibration of plate is more severe, as you can see in this picture. Okay? Right? So overall behavior we do understand. Okay. What if then we have many different vibrations on the wall? Okay? Then I can say that. Interesting. What? Suha, there was some comment? Nothing?
여기서 이렇게 뭘 보고 이렇게 판단하는 거죠. 그림에
뭘 보고? 뭘 보고? 어?
희미해진 거 보고 됐다 이거 판단하는 거.
아, 희미해진 거. 야, 여기는 여기서 I'm sorry, I have to speak English. I'm sorry. Okay, the darker means more, I mean, higher sound pressure. Okay, if you can see here, darkness gradually decay, and then this is negative pressure. So if I draw the sign, it looks like this, right? And over here, compare with this and this, it decay. The ratio of decay from here to there getting smoother, right? So I can there say the cancellation effect is very severe in the near field, but as you go in the far field, the cancellation effect is getting less and less, and in fact it looks like a monopole behavior. Okay, acceptable? And over here, comparing this and this, for example, at this line, it already looks like approach to the far field already. Already smooth this side compared with that, because the cancellation effect is more severe already in the near field. As we demonstrated actually when you were absent in the class. I will bring the, why don't we bring the speaker again for the special students. Maybe it's not just for you, but every student want to experience those things again, right? Right? Okay. So, in fact, what you commented was correct. I argue that based on the graph we had. Okay. Now, what I can argue that the pressure due to, for example, the vibration of this kind of plate can be written in Cartesian coordinate. Like I have a pressure magnitude. Right? No objection, right? And I can write see very carefully. Right? And because this has to satisfy this governing equation, therefore we plug this one over here, and I have